Okay. All right. In our last lecture, we started talking about modified equation to analyze the behavior of numerical schemes. So we started by looking at the upwinding scheme for solving the simple differential equation du dt plus du dx equal to 0, which is a linear advection equation. So the solution we know is a waveform that travels towards your right with no modification in the shape of the wave, right? And yet, when we solve the differential equation using an upwinding scheme, we know that the solution is going to be decaying, especially for high-frequency oscillations. And this can be analyzed using the modified equation analysis. So if we solve this differential equation by discretizing the spatial derivative using an upwinding scheme, which is ui minus 1 divided by delta x equal to 0, right? So this is the upwinding scheme. We can see that this is a first-order discretization of the original differential equation. So the difference between them is first order. But through a Taylor series analysis, we can find out that the numerical scheme is actually an even more accurate discretization of a modified equation. So it is actually a more accurate discretization of the equation that I'm going to write below, that is equal to delta x divided by 2 times the second order derivative of u. So it is a at least a second order discretization of this equation. So what's the difference between the original differential equation and the modified equation? By the way, this is called the modified equation. Is that there is an additional second order derivative term, which is actually numerical dissipation, right? So we know that addition of this term, like in the heat equation, actually diffuses particularly the high order components, right? So this behavior can actually be very easily illustrated in MATLAB by coding up a function. So if we code up a function that is du dt, we are going to return that as ddt is equal to this. So we are going to use the same periodic domain to illustrate the problem. So the input argument is t and u. So again, we're going to be using ODE45 to solve the discretized equations. Okay. So basically, the upwinding is going to be first of all, du dx is equal to u minus and ui minus 1 can be written as u from 2 to end and u1, right? So this is assuming u is a row vector, which I'm not sure if ODE45 gives me. So I'm going to change it if it doesn't. So divided by dx. So of course we have to compute dx, and let's assume our entire domain is 2 pi, then it's divided by the length of u, right? And the ddt then is equal to minus du dx. So that's basically what this differential equation tells me. All right. So then if we initialize the solution, u0 is equal to 0, let's say give it 100 grid points. Actually, I think I have to do this. Okay. And u0, let's just make some portion of it from 40 to 60 equal to 1. Okay. So which is a square wave to start with, and if we plug this into a ODE45, du dt, and I think is it the time domain first, 2 pi. So basically we add back for one entire period and u0. So let's see. Okay, so that means I was passed in a column vector. Let's do that and try again. Okay, so we get a U that is 309 is the number of time steps it took, and 100 is the domain size. So okay, so let's plot U, and okay, so this is actually plotting the solution as a function of time, but like we actually want to plot U prime, which is the transpose of U. So we can see that initially we have a square wave. So that's basically, if you look at this wave, it's the initial condition. And it seems that the solution, is it advecting towards the left or towards the right? So let me see. Maybe did I have a coding error here? So I have U minus UI minus 1, ddt is equal to that.
UI minus UI plus 1, that's the way you put it? Yeah. It should be U and minus.
Should be, sorry, are you referring to here?
Yeah, this term is negative.
So UI minus 1 is upwinding from the left. And in my implementation, so this is UI, and this is UI minus 1, which actually is wrong, right? Thank you. So it should be from here, and yeah, so U and that, right? So this is the proper, huh? Yeah, thanks. Okay, yeah, so this is UI minus 1, right? So at the first grid point, I minus 1 is actually the very last one, right? So okay, so let's run this again. Okay, yeah, so need to change this to vertical concatenation, and let's plot this again. Okay, so now this time I think the solution is right. Initially we have a square wave that travels towards the right, and this is the final solution. It looks more like a Gaussian than a square wave. So this is the numerical dissipation in action, right? The amount of dissipation I have in the system is half times delta x. Right. So this additional term. Do we remember how it came out? It is by basically doing the same Taylor series analysis to analyze the accuracy of the scheme, but keeping more terms and leave it in the equation. Right. Okay.